Welcome everyone. This is great. Looks like over 130 people connected. Well, I would like to keep the session as interactive as possible. So if you have questions, definitely ask in the chat, and I'm definitely happy to take questions at any moment. And yeah, as for these 4 lectures, it's supposed to be on probability theory. It's supposed to be a rigorous introduction to probability theory. Now, why rigorous? It's simply because often people do get some understanding of probability theory, and they proceed to become data scientists, machine learning researchers, machine learning engineers, and so on. But if they didn't actually spend much time thinking about the fundamentals of probability theory, then it may be a little bit hard for them to actually read academic papers on statistics, all sorts of data science related subjects, and yeah, definitely the advanced parts of machine learning. They do require some very good knowledge of statistics and probability theory. So yeah, in these 4 lectures, I would like to introduce the concepts, introduce the mathematical definitions, and I would like to make sure that people who joined actually understand how to use these concepts, how to do some calculations. We will not get excessively far, so there will be definitely big areas of probability theory that we will not even touch. But yeah, I would like to make sure that everyone understands very well the basic fundamental concepts. And yeah, maybe I can share my screen here. If you are curious about what kind of things that we may be talking about in this series, well, it will be some introduction, different kinds of probability distributions, something that we should talk about at the beginning. And let me see. Okay, yeah. So we will talk about the different types of probability distributions. This will motivate us to actually think about some rigorous mathematical framework for all of this, because there are actually some mathematical paradoxes that you would run into if you do not define things properly. So we would definitely want to be able to talk about discrete and continuous distributions and anything in between. And we need to organize things in some good way. We will need to define some mathematical concepts that are listed here. So this is more on the fundamental side. And then once we get further, we will talk about things that are actually very practical. So concepts like probability mass functions, probability density functions, cumulative distribution functions. So all of these are used all the time. They are very useful. And yeah, it turns out that people who did not actually spend much time on probability theory may have trouble manipulating these objects. So yeah, I would like to make sure that people understand how to transform these basic properties of distributions and random variables and so on. So yeah, there will be the lectures, and also there will be some resources that you can use offline. Let me get here to the context. So first of all, you can sign up for quizzes, homework, and notes and stuff like that. And I have a link here. Maybe I can share the link also in the chat box. So if you follow this link, there will be a simple form. Just a second. Yeah, there will be a simple form for you to fill out. And then basically a form, like type form asking you for your name and for your email. And then, you will receive emails about the different quizzes, pieces of homework. You will have access to the kind of notes that I have right here, and so on. Yeah, as for contacts, so on Twitter, you find me at this handle. So that's my last name, Fabinger. And as for the school, the Acalonia school, it's this Twitter handle. And also because it started as Tokyo Data Science, this one. So feel free to contact me, definitely. You see my email in here as well. And yeah, we can talk on Slack and so on. I would like to make sure that all of the concepts that we discuss are entirely clear. I have actually two side notes to mention here. So side note one, some students that I worked with and I wrote recommendation letters for, got into PhD programs at pretty good universities like Stanford and Princeton and so on that I mentioned here. So if you are actually interested in graduate programs, I think I do have some advice to give you. So in that case, feel free to contact me. But the thing is, in order to actually get to some top PhD programs, you do need to understand the math as well, right? So you need to definitely understand the kind of concepts that we will talk about in these couple of lectures. But yeah, if you are interested in applying soon or later, let me know. And also, maybe you would like to work remotely as a research assistant for some professors at some very good universities. In that case, you can also let me know. So I know a lot of people who would really want to have talented research assistants, and yeah, it's possible to do it remotely, right? So you can be, for example, in a developing country, and you can get paid for work that you do online, working for some professor, say in the US. So these are some side notes. But here, really, I should emphasize that if you want to do some serious work, some serious research work, knowing the fundamentals of statistics is a good idea. So that's what we should discuss next. To get started, let me just mention types of probability distributions. Probably a lot of you have had some exposure to probability theory, maybe not at this kind of rigorous level that we will have, but intuitively, you probably understand a lot of things. So maybe you understand things like the Poisson distribution. Here is the probability mass function of a Poisson distribution. And yeah, if we plot things like this, basically the height of these individual dots in this plot would signify the probability that a particular value happens. So yeah, for value 5, you have this height in here. So yeah, that is this kind of discrete distributions, that have the probability concentrated at individual values. Of course, you can change parameters of these distributions. We will talk about things like that later on in some of the following lectures. So that's a discrete distribution. Maybe you know the binomial distribution. So this would be a distribution that would count the number of heads that you obtain if you make, say, 20 coin flips. This is the distribution. When you have a fair coin, if you have a biased coin, the distribution is going to change in some way. And yeah, this is another discrete distribution. In the first case, in the case of the Poisson distribution, there were actually infinitely many possible values. In the case of the binomial distribution, you can actually get just a finite number of values. But in both cases, this would be some discretely distributed random variable. Now, of course, we also have continuous random variables. You probably know the normal distribution. A normal distribution would have a PDF like this. So PDF is the probability density function. It's a continuous function in here. You can change the parameters of the distribution. Maybe you change the standard deviation to make the distribution more dispersed. You can decrease the standard deviation parameter to make it more concentrated. Yeah, any real value is possible as a value of a normally distributed random variable. So these concepts individually are actually pretty simple. You don't need some super advanced math. You don't need some very rigorous framework for probability theory to deal with this. But in real life, you actually often meet also distributions that are kind of in between. So in that case, things get a little bit more complicated. Maybe we can call these mixed distributions. So distributions that are neither discrete nor continuous. I don't think mixed distribution in this sense is very commonly used, but I will use that for distributions like the following one. Yeah, let's think about one particular case. Let's think about the distribution. Maybe I can actually follow this link here. Yeah, let's think about the distribution of gross nominal hourly earnings in the UK in 2016, specifically for male workers. If you take a look at that, you would see a plot like this. So on the horizontal axis, this would be the wage in pounds, and on the vertical axis, you have some measure of frequency. So how many people actually had that particular wage level. And in here, well, it doesn't look exactly like a discrete distribution. Conceptually, it doesn't really look like a continuous distribution. It will be something in between, something that will motivate us to actually build some mathematical objects in here. First of all, let me ask you, do you have an opinion on why the wages are actually distributed like this? So you see very few cases of wages being very low. Then you have this spike, and then you have something that looks like a continuous distribution. Yeah, so people say minimum wage. Also, incorrect data. Well, in this case, I think the data is probably correct because the government needs to collect the wage data. They collect that in order to then get tax payments. So yeah, you may think that probably this data is fairly reliable. But yeah, the minimum wage, that is definitely an issue. So the minimum wage is actually the reason for this spike in here. Let me highlight this. Yeah, so this spike in here, that is actually related to the minimum wage. The minimum wage was about £7 per hour around that time. So it kind of makes sense that you will have a lot of people at that level. And let's see. Yeah, then we will have definitely people who have more than the minimum wage. That would be here, maybe £10, £20, and so on. How about below? So does anyone have an idea why we are actually getting values of the wages here that are below the minimum wage? Okay, yeah, so the closest was interns. Yeah, that's right. You will have some apprenticeships. So the minimum wage does not actually apply to everyone. If someone just wants to gain experience, a young person, for them, the minimum wage law is not going to apply. Now, let's ignore that for a minute. Let's really think about just the people who are subject to the minimum wage. So let's ignore for a moment the left part of this distribution. And let's think about how to model this stuff. How do we actually mathematically describe this distribution? Well, in that case, I think it makes sense to consider a mixture distribution. Specifically, what I have plotted here is a mixture of an exponential distribution and a single probability mass point. So the orange part that corresponds to the minimum wage, idealized. The blue part of this plot corresponds to some exponential distribution. Now, why did I choose exponential distribution? It's just that I looked at the data and it was actually a pretty good fit. Some of you suggested Pareto, and yeah, Pareto does apply to some parts of the income distribution often. It's not a perfect description of the distribution of wages in a country, but yeah, in some parts, it's good enough. For this particular plot, for this particular data, an exponential distribution worked just fine. So that's what I chose here when I made this idealized plot. And yeah, in this plot, you see one discrete distribution. So that's the orange part. And that corresponds to a random variable that has value always equal to 1. So let's say that the minimum wage is equal to 1. In this case, for this particular value, I chose actually 50% of the people to be at the minimum wage, 50% above the minimum wage. In this plot, I can change this. So I can suppress the number of people who have the minimum wage. I can increase that. So yeah, if we go to this extreme, everybody who has some labor income would be subject to the minimum wage and would exactly earn the minimum wage. If we are in between, yeah, you will have some people earning the minimum wage, described as a real distribution that's centered, that's supported just by 1.1, and then the rest of the distribution. The rest of the distribution is a continuous distribution. It really does make sense to think of this conceptually as really a continuum. And yeah, as I said, the exponential distribution actually fits well. If you take this together, then the distribution overall is neither discrete nor continuous. So we need some mathematical framework that would allow us to easily talk about things like that, these kind of mixed distributions. And yeah, so some questions were here. Should we think about the noise? And yeah, of course, there is some noise involved. For this particular picture, I did not really think about that. And I also ignored the people below the minimum wage. This is just for us some motivation to think about these mixed distributions and some motivation to build some mathematical framework. Now, if you think about it, if you only had discrete distributions, then you could build your probability theory just using summations, right? You would use the summation sign in your formula, you would be fine. If you only had continuous distributions, then you could build your probability theory using integrals, and that would be also fine. But if you have both of these things happening at the same time, then the kind of formulas that you would write would become actually really, really cumbersome. You would have to explicitly take into account that some part of the distribution is discrete, some other part is continuous. So you would end up with formulas that have both sums and integrals. That's very inconvenient. Also, in some mathematical models, you don't know in advance what kind of distribution you get in the end. So having to deal with summation and having to deal with integration all the time and just distinguish it at any time in any formula, that would be inconvenient. For us, we are going to deal with this by defining the so-called probability measure. we will have one concept, probability measure, that will be applicable to both discrete and continuous distributions and their mixtures. So yeah, if you want to describe situations like this, it's much more convenient if we build some solid theory, define probability measures, and then we should be just fine. So it will be a little bit boring at the beginning. It will require some building of mathematical framework, but it doesn't actually take that long. And if you keep reading papers on statistics subjects for years, then definitely it's an investment worth making. All right, so now let's go further. And I have some comments here. So why do we need the rigorous framework? Well, I think I just mentioned this, but let me also explain why things will be a little bit complicated. Well, it turns out that if you deal with continuous spaces, they can have some paradoxical properties. So mathematicians work very hard on establishing some solid theory of real numbers and spaces of real numbers and so on. But some things may not actually be working exactly the way you would imagine intuitively. So if you want to work with continuous spaces, you should be aware that some things are a little bit weird. I'm not going to spend that much time on it. I'm just going to tell this to you so that you understand that we actually do need to build some theory that's solid. So there are some paradoxes. I listed them here. You can follow these links in the notes when the notes are posted. But let me mention this one paradox in here, the Banach-Tarski paradox. So this is the Wikipedia page. It turns out that if you take a three-dimensional ball, then you can split it into multiple pieces, a finite number of pieces, in such a way that if you split it and just move the pieces around and rotate them, you can use them to assemble two spheres, two balls like this, that have the same volume as what you started with. So when it comes to continuous spaces, when it comes to real numbers, things can get pretty weird when you start thinking about volumes, when you start thinking about measures. So this is something that we want to avoid. It's a very, very weird result, but proven by mathematicians. This is what we really want to avoid. So we will spend some time building theory to make sure we don't run into some wild stuff like this one. Yeah, let me also comment actually on physics applications. So some of you may have studied physics and quantum physics and so on. So if you think about quantum theory, you would often use a theory of distributions built by Lawrence Schwartz. So Lawrence Schwartz, he developed this theory of distributions that actually formalizes the notion of the Dirac delta function and its derivatives. He got his Fields Medal in 1950, and the framework is very, very useful in physics. Now, this is way more complicated than what we are going to talk about. We don't need something that's worth a Fields Medal. We need something relatively straightforward that I can explain in a lecture or two. So yeah, let's jump there. So yeah, our strategy for avoiding the paradoxes will be the following. We are going to have some sets that we will just ban. There will be some subsets of the real line of real numbers, some subsets of continuous spaces to which we are not going to assign any probability at all. So I call it band. That's not the official term, but yeah, we are going to forget about sets such as those that show up in this Banach-Tarski paradox. And when we work with this theory that we built, we are going to have some sets that are allowed. So there will be some regions that will have probabilities assigned, and they will need to satisfy some intuitive properties. So if region A is allowed and region B is allowed, then also their union should be allowed, and so on. So there will be some intuitive concepts, intuitive properties that we will require. And this will be related to what we will call the sigma field. I will probably not elaborate on the sigma field too much today, because I have even more basic things to describe. But yeah, I just want to tell you that the way we deal with the paradoxes is that we are going to avoid the wild sets. We are going to work with sets that are much more tame. And yeah, then we will not run into any trouble. So that's actually some explanation for why we actually want to spend some time building theory. So yeah, one thing that we need to think about is how are we going to organize the mathematical objects that we are going to work with? And yeah, if you think about it, if you have some probability theory, you should have some things that are random. But here we will actually distinguish between two kinds of mathematical objects. So some mathematical objects are going to capture the randomness. They are really going to represent what's not deterministic in what we are considering. So a lot of different things can happen in the real world. There will be some randomness. We are going to capture all of that in one type of mathematical objects. And the rest of it, some calculations that we are going to do, that we are going to make based on the random objects, yeah, they will be separate. So there will be some deterministic consequences of whatever happens. Today, we will talk mainly about the concept of the probability space. So this will really capture the overall randomness. If we build some model, there's randomness, we are going to capture all of it in this probability space. And then there are some computations that we can make on top of this randomness. And yeah, this will be object deterministically derived, and these will be random variables. Most likely, we will talk about random variables next time. Probably I will not have enough time for today. Yeah, just to give you examples. So if you have, if you are in the labor market and you receive some wages, you can say that the wages are the kind of random object, the fundamentally random object that that you want to capture. And then taxes. So you may need to pay some taxes to the government. Well, these are going to be deterministically derived. So your wages in this case would be captured in the concept of probability space, and the taxes you pay, they will be captured by random variables. Or maybe you consider a soccer game. So in the case of a soccer game, you can keep track of the overall score. That will determine what actually happened. And then you can build one more variable that will tell you who actually won the match. So the second variable, that will be the derived object. And yeah, you can build some complicated meteorological model of the atmosphere. That will be the random thing. And then you can decide to calculate the average temperature in Tokyo at some predicted, at the predicted time. That will be a derived object, and so on and so on. So if you do some coding, maybe you have some random number generators in the code. And then you will have the rest of your code actually being deterministic. So today we will really talk about objects number 1 in here. Okay, so here are some mathematical definitions. We are going to define the probability space. So that really is designed to capture the randomness for us. Now, what is probability space? The term is actually kind of weird. The probability space is actually 3 different things combined into one. Now, I think I should, for each concept in here, to say what it means simply and intuitively, and then I should go through the mathematical definition. So specifically here, for the probability space, the probability space is the set of mathematical objects that we need to define in order to meaningfully talk about probability in a particular situation. So it will be actually 3 different things. This is capital omega, capital F, and capital P. The capital omega, that's going to be the so-called sample space. It will be the collection of all possible outcomes omega. So little omega is an outcome. For example, the final score of the soccer game, that could be a little omega. And capital omega, that would be the set of all possible scores that you can possibly have for that game. Then we will have an event space, or you can say it's a class of events. So these will be the kind of events to which we want to assign some probability. I will talk about the details, but an event is something that should have some probability. And then finally, we will have this probability measure P. So that one is going to give you the probability of a certain event. Now, these objects need to satisfy certain conditions. I will definitely elaborate on it in a second, but at this moment, there will be 3 things to consider: the sample space, the set of possibilities of what can happen, then event space. Now, this will be this will be collection of events to which we assign probability, and finally, we have the probability measure. So I'm going to elaborate on these 3 objects. As for the sample space, it's not terribly complicated. As I said, it's supposed to be really the set of all things that can happen. And if you just roll a die, you have 1 roll of a die, then you can get these numbers, 1, 2, 3, 4, 5, 6. So in this case, the sample space, capital omega, is just this set of 6 numbers. Now, if you want to think about the sample space for rolls of 2 dice, it will get a little bit more complicated. So let's say on the first die, you get the number 2. On the second die, you get number 1. In that case, the outcome, little omega, is 2, 1. It's this pair, 2 and 1. And the capital omega, that's going to be the set of all possible pairs like this. I just wrote it here. And it has 36 elements in total. Obviously, if you have more random stuff going on, you will need to have a larger sample space. So these are discrete. You can also have a continuous sample space. For example, if you're thinking about temperature, so the temperature is going to be some positive number, so number between 0 and infinity, and that's again a valid sample space. I'm getting questions. So should the sample space be finite or infinite? It's up to you. So if you can capture everything in a finite sample space, then definitely do that. But for many applications, you just do need some continuous sample space. For example, if you randomly measure the temperature, you definitely need any real number in here. Or you can think about economic outcomes. Let's say that we think about all possible economic statistics in the world tomorrow at 2 p.m. UTC or something like that. Yeah, that will be our sample space. And then we can do some computations using this sample space. Now, obviously, in this last example, it really matters how you model things. If you build a complicated mathematical model, you will probably have a bigger sample space. So thanks for the question. And yeah, as I said, later we will define random variables. And the random variables, they will be actually functions. So they will be functions of these outcomes. Okay, so that's the concept of sample space. Hopefully this is clear, but if it's not, let me know. And then another concept will be the concept of events. So what is an event? An event is actually a collection of outcomes. So it's going to be a set of outcomes. And then to this set of outcomes, you will assign some probability. So for example, if you have one roll of a die, then this is the sample space as we discussed. And yeah, what if you want to define an event A that will correspond to getting an odd number for your roll of the die? Well, in that case, it's going to be this particular set, 1, 3, and 5. These are all odd numbers. And if you make a set composed of them, this is really the event of getting an odd number. So we will have these sets of outcomes. They will be called events, and we will define probability for them. Or if you have rolls of 2 dice, then, yeah, as I said, we will have this more complicated sample space that will have 36 elements. And we can think about an event that corresponds to getting number 1 for the first die. Well, it's these 6 possible outcomes, right? So we get number 1 for the first die and any other number for the second die. And that's important to understand. There's a distinction between outcome and event. An event is a collection of outcomes. It can have one element, it can have more elements, but definitely an event is a set of outcomes. It's not an outcome. And then, yeah, in the case of temperatures, you can think about the event corresponding to having temperature outside above 303.15 kelvins. Well, in that case, your event is actually this whole set. It's this interval from 303.15 all the way to infinity. So that's events. And I will define a couple more things here. Yeah, the event space, yeah, or you can say class of events. I said that we may want to just pick certain subsets of the sample space to work with. Not in all cases, but in many cases. And we will basically pick those events that we like. We form this event space. So the event space, this will be the set of subsets of the sample space for which we are going to define probability. Now here things are getting a little bit more complicated, but yeah, hopefully this will not be too complicated. If you have just one roll of a die, you can definitely consider all possible subsets. So you can take any subset from here, and you can say this is going to be your sample space. You are going to assign probability to each one of these events. And the number of events in this case is 2 to the power of 6 or 64. So in this case, if you consider all possible subsets of the sample space, it would be called the power set of the sample space. Yeah, that's something that is possible, that is practical if you have a discrete sample space. Now, when things get continuous, it gets more complicated. But yeah, here we are basically claiming that for any possible subset of the sample space, we are going to go ahead and define probability. So we include any subset in here in our event space. But we don't have to. So if we want to be more restrictive, with the exact same sample space, we can just consider smaller number of events. Maybe we just pick four sets like this, and we define probability for those. So in that case, our event space has just 4 elements, and we will be able to meaningfully talk about the probability of getting number 1, or the probability of not getting number 1, and so on. But for some other events, or like potential events, we are not even going to define the probability in this case. Now here, it may sound kind of weird, but it is something that we will need to do in the case of continuous spaces. So yeah, let me jump back. Yeah, if we end up, if we start working with real numbers, and the outcome space is actually from -infinity to infinity, as you see here, then we do need to be picky. It turns out that if we did use the power set of this real line, if we use the power set of all real numbers, that kind of set would be a little bit too big. It would include some of the sets that have these paradoxical properties. So in the case of continuous outcomes, in the case of continuous sample spaces, we do need to be picky. We need to pick only certain subsets and then work with them. What I want to say at this moment about the real numbers is that we will be allowed to talk about probabilities corresponding to sets like this, like a single number or 2 numbers, or an interval, an open interval between, say, 301 and 305, unions, closed intervals, things like that. So when we form our event space, it is going to include all of these things that intuitively we would like to have, but it is not going to include some of the sets that you would consider paradoxical, like related to the Banach-Tarski paradox. We will talk about it in more detail the next time, but let me say that for real numbers, we will have this particular event space that's called the Borel sigma field, also called Borel sigma algebra. I will elaborate on it the next time, but yeah, for now, let me say that things will be slightly complicated, but not horribly complicated. And yeah, kind of the final thing that I wanted to say today was about the probability measure. But before I get to the probability measure, any questions about the events or the event spaces, classes of events? Okay, so I'm getting a question. Event space basically depends on definition of our event. Is that correct? Exactly. So even if you specify one particular sample space, so the set of all possible outcomes, you can still decide which subsets are going to be assigned probability and which you are just going to ignore. And then for those subsets for which you want to define probability, so these subsets you will include in your event space, and you need to satisfy certain axioms, certain requirements. So we will talk about the requirements, but yeah, I think I should jump here to the concept of probability measure. Yeah, so I'm getting a question about probability measure. Yeah, let me jump to probability measure. So quickly, the probability measure is going to be an assignment of real numbers, probabilities, to these different events. And yeah, rigorously, let me say that, let me maybe read this. A probability measure P is a function that assigns a real number to every event from the event space and satisfies the following three requirements. Yeah, actually, besides that, there are separate requirements for the event space. We will talk about them. But these three requirements I have right here, they are requirements for the probability measure. So if you want a particular function to be called probability measure, you need to satisfy the following. So for any event in your event space, the probability just cannot be negative. So P of A is greater or equal to 0. Then if you think about the probability of the entire sample space, that probability has to be equal to 1, meaning that the sample space actually does capture all of the things that happen. There must be 100% probability that one outcome from the sample space actually happens. And then we have the third requirement, which is a little bit technical, but actually fairly intuitive. So let's say that we have some series of events. We can organize them here. I actually wrote series, but I meant sequence. We have a sequence of events, A1, A2, A3, A4, and so on. And let's say that these events are pairwise disjoint. So it cannot be that two of these happen at the same time. Well, in that case, the probabilities need to add up. On the left-hand side, I have the probability of a union of all those events. So that's the probability that anything from this sequence happens. And on the right-hand side, I have the sum of probabilities of these individual events. So I guess we should talk about that next time. I'm running out of time. But it's something as simple as, yeah, you think about the probabilities of different colors for a traffic signal, right? If you have probability of a red equal to 30%, and you have probability of green equal to 50%, then the probability of red or green must be equal to 80%. So this is the kind of requirement, something very intuitive, even though it looks complicated using the mathematical symbols. Yeah, the next time I will definitely need to unpack this a little bit. I will need to talk about the requirements and provide examples of what happens. We should talk about the requirements for the sets of events, so for the event spaces. And yeah, there will be also a quiz. If you sign up for the quiz, then you will receive an email. You will receive a quiz. If you actually complete the quiz, it means that you understood the main concepts we discussed today. And yeah, again, if you joined a little bit later, I can share the link to that sign up in a second. But yeah, so before we stop the recording, any questions you would like to have on record? Then we will have some informal questions after that. All right, yeah, it's a lot of concepts. We will continue next time. I will provide some more examples in intuition. And yeah, the next time we should also build some more theory to make this whole framework practical and useful for actual computations. Okay, yeah, so the link again, well, it's this one, but I'm going to share it again in the chat. All right, yeah, so thanks very much for joining.